My name is Lowell Gustafson. I'm Chair of Political Science, and I'm delighted to have Dr. Philip Maurone here kicking off our year-long series on anthropology called In the Beginning. I asked him the virtually impossible task of talking about the question, how did the universe begin? And I'm glad that he gets to explain it rather than me. But I also wanted to thank Dr. Barbara Wall and the Office of Mission Effectiveness for sponsoring this series. And the reason we're calling it an anthropology series is that because throughout human history, virtually every culture known has asked this question, is where did all this come from? Where did the sun and the moon and the stars and all this around us? And each culture has come up with the most marvelous explanations or stories about all of that. But virtually none of them match the story that physicists and astronomers have developed over the last century, which have transformed our notions of where we are in time and space and how we understand virtually everything around us. And it's been an exciting story, which those of us over here on the art side of the house have some small inkling, just enough knowledge to make us dangerous. And so we're very appreciative when those of you from Mendel come over and set the record just a little straighter. So thank you, Dr. Maurone, for coming, and thank you for all being here.
Thank you, Flo. Well, this is an incredibly difficult problem. There's no question about it. You know, the mathematics is just impossible. Formulas are just impossible. I may use the F word once in a while. Formula. But we can answer this question without a lot of mathematics and without a lot of formulas. Let me see if I can go through this. How did the universe begin? Without math, without a lot of formulas. I don't know. Nobody really knows how it began. So that's the short answer, all right? And it'll evolve. The idea of how it began, and even the question, I think, will evolve. When was the beginning? What does the beginning even mean? Okay, physics, I was talking with Lowell before we started, in the last century never talked about answering the questions why. That was too philosophical. Well, they're starting to talk about those kinds of things. Why this universe? And why this kind of beginning? Why did the parameters choose this rather than that? So people are talking philosophically about the beginning times. So if we don't know how it began, what do we know? Okay, I'll have to stand out in front here with you guys to read some of this. We know how the universe evolved from about 10 to the minus 44 seconds to now. Why did we pick that number? That's a crazy number, isn't it? We know that pretty precisely, actually. But the 11 billion years later, which is where we are now, that has evolved. It was 15 billion, it was 12 billion. It may even be a little less than 11 now. What's it, 10.5 billion? In that neighborhood. That number changes as we get more information, but the 10 to the minus 44 seconds doesn't change. We can't go before that, to the instant of the Big Bang. The size, we can go from when the universe was about 10 to the minus 35 centimeters. If you can imagine that number, that's 1 over 10 and 35 numbers there. Okay? Incredibly small. It's 1 trillion trillionth of a centimeter. Okay? And imagine that all the mass that you now see is in that space, if you can imagine that. How do you talk about a space like that? But we can go from there to where we are now. Our theory of gravity, our theory of electricity, magnetism, and some other theories carry us. As Lowell mentioned, how do the stars form? How do galaxies form? We think we know that. We think we know what happened from here out. We know how stars, solar systems, and galaxies form. We know the energy source of stars, in fact. In the last century, we discovered what the energy source of the stars is. Hydrogen bomb, really. basically, is what the mechanism is. Hydrogen bomb. We know that. We've discovered that. We reproduced it here. So we know that. That's kind of incredible if you think about it. We know the energy source of the universe, really. We know there are 4 forces in nature, and they may be unified at early times or high temperatures. Turns out that that's the same thing. As you increase the temperature or the energy of probing the microscopic world, you start to approach what happened in the early universe. So they are connected, okay? The study of the forces around us right now with the early universe. So this is the way I'm going to try and proceed here. I'm going to talk about some cosmology, which is the study of the whole cosmos, the very large. We're going to talk about the very large. And high energy physics, which I specialized in some years ago. And that's the search for the fundamental building blocks of nature, or the fundamental forces in nature. And it's usually the realm of the very small. As time went on, people started to look at smaller and smaller entities. First it was molecule-sized things. Then we discovered that we can look at atoms. Then we can look inside atoms. And then we can look inside the nucleus of an atom. So it progressively got smaller and smaller and smaller, our focus. Turns out that that focus is approaching 10 to the minus 34 centimeters. And it turns out that's why the Big Bang limit is so very well defined that way, because of particle physics is banging into that same problem. So particle physics gets joined with cosmology at that end of it. The very large and the very small become one at early times in the universe. Never the twain shall meet. I'm afraid they will. That's the point. All right? They will. The very small and the very large, the cosmos, are meeting right now. Okay? The same people who worked on particle physics are working on cosmology now. I want you to remember these numbers. The 11 billion years, the 10 to the minus 35 centimeters, roughly 1 trillion, if I say enough, trillionth of a meter, incredibly small length, and 10 to the minus 44. I'll try to justify or explain why those numbers are the way they are. That's the why talk about. And the speed of light is another interesting number. It's 3 times 10 to the 8 meters a second, or it's 186,000 miles an hour. A second, sorry.
No.
An hour. Second, hour. What is it? Second. See this thing messing up my memory here. This number here is rather interesting. Although very large, very, very large, the nearest star to us is about 24 trillion miles away. It takes light 4 years to get here from there. But yet this is the ultimate speed in the universe. Why is it that speed? I don't know. It's kind of interesting. Most things have speed limits. Your car has a speed limit. And it comes about from the way it's made. It has a certain speed limit. Well, the universe has a speed limit. This is it. Nothing can go faster than that number. Although very large, not large enough to span large places in our galaxy even. Near a star, light takes 4 years to get here from there. So when we're looking at that star, an interesting thing to just remember is why I want you to remember this number. What you see is as it was 4 years ago. So when you look into the night sky, you're looking into the past. The farther you look, the earlier you're seeing. And right now I believe the limit is about the 11 billion years. We're starting to see close to the beginning. We're looking far enough back in time and far enough away that we're seeing hints of the beginning scenario. All right? Kind of really fascinating, I think. Okay, I want to talk about the force laws. So we're going to look at what we talk about today and things we're familiar with today and see how it couples back to the beginning time. So I want to talk about the 4 forces and how they came about and what we do with them. Okay, just to give you a little taste of what it's all about. Gravity is the first one. We're all familiar with it. We live in it. We're used to it. And we don't question it usually, okay? Newton, who gave us the law of gravity, actually brought together the motion in the heavens with the motion near the surface of the earth. At one time, people thought the motion in the heavens, understanding it, was unattainable. Well, we'll never understand that, so why bother? Excuse me. And if you look back at some old manuscripts, before the time of, for instance, Galileo, Kepler, Copernicus, around the time of Tycho Brahe, you'll see models of the universe. And it's the Earth-centered, okay, geocentric. And you'll see the Earth, and then you'll see planets, you'll see the sun, you'll see these things going out and out and out and out. And then you'll see the stars in these models. And then you'll see the hand of God out there, because I have my keys with me now. I locked them in my office earlier. This wasn't good. By our nature, when something moves, we look for a reason. Even though we're talking about motion in the heavens, and it's not for us to know that motion. It's God's information. We're looking for, if something moves, we look for the reason. Where's the touch? What touched it? So, interestingly enough, all the planets are on these crystal spheres as the model. Glass, they're on these glass spheres. The planets are stuck in these spheres. The spheres are connected to one another by cogs, and God only has to move the outermost one to start the whole universe moving. So even then, we were forcing on God our requirement that motion requires a cause and a touch, a direct touch. If I were to wiggle my fingers and the keys move, you would want to run up and see where the connection was. You'd think it was a magic show. Where's the connection? Okay, but yet, gravity is such that if I let the keys go, the keys are going to fall to the top, and everybody accepts that. But it's only in the last 50 years, 40 years, that we know if you're in a spacecraft and you leave something go, what happens to it?
It can actually float, right?
It just stays there, right? It just stays there. You let go, it stays there. How can the Earth, without touching the keys, like, how can the Earth pull a key? That should puzzle the hell out of you. Same with the magnet. I come with the magnet here, and I get close enough to the keys, and the keys jump up to the magnet. How did it do that? It didn't touch them, but yet we require a touch, a direct touch. And that does need to be explained. How can the Earth affect the moon? How does the sun affect the Earth? That's why the ancients needed the crystalline spheres. When Newton came along, he said, oh, it's gravity. Well, that's still not good enough. What is it that's going on between the Earth and the moon that causes this attraction that Newton calls gravity? We need to talk about that. Electricity and magnetism. We're not so familiar with that at times. Okay? So, you can be familiar with magnetism. You can dig stones out of the ground, and it'll have funny properties and make bits of metal move in certain ways. You're a little bit familiar with electricity. If you rub a balloon and stick it to the wall, that's certainly different than gravity. See, the point I want to make here is there are four forces. Why do you need four? Is there something different than gravity? Yeah, there's this other thing with this balloon. It sticks to the wall, or with a magnet, it jumps the keys. Now the Earth's pulling them down. This little chunk of metal's pulling them up, what we call a magnet. It's got to be different than gravity. So there's another force out there that we need to investigate. Electricity and magnetism is the other one. There are two more that I really can't talk about until we actually go to the next couple of slides. Here are the other two. I'm just going to list them. One is called a strong force, and the other is called a weak force. Leave it to a physicist to be creative with the words, right? Strong, weak. The strong force actually is a nuclear force, and so is the weak force. Let's go one at a time with these forces here. We'll start with the gravity and ask some questions about it. If we move the Earth further away from the sun, what happens? Does the force get stronger or weaker? Simple question. It's weaker, right? Wouldn't you think? If it moved further apart. That's an intuitive idea. What's the source of the force? What causes gravitational force? What is it? What can feel the gravitational force? Well, we all do, that's for sure. Right? Pulls us down. Well, the distance behavior is a 1 over r squared. It's one of the F words here, formula here. Sorry about that. But don't worry about it. It just says that as the distance grows between two objects, the force gets weaker. That's all it says. The square, that's a whole nother lecture on the dimensionality and the nature of forces. Why is it a 2 and no other number? It has to do with the three-dimensional space we live in, the geometry we live in. I'm not going to worry about that right now, but it's not real hard to understand. Just take from this that as r gets bigger, the force gets smaller. That's all. There is a distance behavior here. What's the source of the force? Mass. What's mass? If you don't know what mass is, don't worry about it. It's the amount of matter in an object. That's kind of not completely accurate, but it's good enough for what we're doing. The amount of material in an object. The number of molecules, if you like. Well, that'll be a preliminary indicator of mass. The amount of stuff you have. There's more stuff in the Earth than there is in the Moon. On the Earth, you get pulled down by a certain amount. You're attracted to the surface of the Earth. If you were to go to the Moon, that attraction is about 1/6. There's about 1/6 the amount of stuff on the Moon as there is on the Earth. So the amount of stuff determines the strength of the gravity, and the distance determines the strength. Closer, stronger, further away, weaker. More matter, stronger, less matter, weaker. What feels the force? Mass. It's one and the same thing. Dual purpose. If it creates the force, it feels the force. And that's a general trend for all the four forces. Whenever you're looking for the cause of the force, if you can find something that feels the force, you found the cause of the force as well. Either way. There's the formula. If it makes you nervous to look at formulas, don't look at it. We don't need it. I already said everything I wanted to say. But we do know the formula. It's simply the product of the masses divided by the distance squared. That's the formula. With a constant out front called universal law, the gravitational universal constant, okay? In some units it's 1, if you pick the units right for your convenience. What I want you to take away from this is the nature of this force. It's attractive. The bodies attract, they don't repel. Right now, anyway, that's what we think. I don't want to get ahead of myself, but there are indications that there could be repulsive gravity. Okay? We don't see it locally here. We're not aware of it. We only are aware of attractive gravity. So that's all I'm going to put. The biggest thing is, this is the reason for the large-scale structure and stability to the universe. Okay? You have large gas clouds that form our solar system, collapse into the sun and planets, and it's the gravitational trade-off and the motion of our solar system that keeps it stable. The sun is attracting the Earth. The Earth, its initial speed was around the sun. There's a balance going on here, and it's gravity that maintains the stability and structure of the whole universe, actually. All right? Next force. It's going to be the same slide, but only for electricity and magnetism. I don't know why that keeps coming up like that. I'll touch them. Again, distance. What's the source of the force? The distance is the same. It's still, the electric force gets weaker the further apart the constituents are. What are the constituents of the electric force? What's the source? What's the receiver? Benjamin Franklin's electric charge that he experimented with. If you ever went, anybody ever go to the Benjamin Franklin Bridge here? You see the statue of Benjamin Franklin with the kite out there, trying to collect lightning to check his theories of electricity. Anybody ever see that? Do you see that? I don't like it. Do you like it? I don't like that statue. Do you like it? I don't like it.
Actually, I've lost count of how many times I've been over that bridge. I've never seen it.
You never saw that?
No, where?
You're lucky. It's ugly.
Is it eastbound or westbound when you go?
It's on our side.
Oh, there you go.
Westbound. For the Benjamin Franklin side, come on. I lived on this side of the bridge. They would never put it on the other, on the Jersey side. It's either a white horse or a black horse on the Jersey side.
Okay.
All right? Those who live in Jersey understand that. So. Electric charge. What is electric charge? It's like mass. It's a property of matter, okay, that gives rise to a force that's different than gravity. That's the best I can tell you. What is really charge? I don't know. I can say the same thing about mass. What is mass really? Why does it create an attraction? Why are these keys attracted to the floor? I don't know. All right? Just don't know. But there's a property of matter, mass, and then charge, that generates two different forces, and it's inherent in the nature of matter. Again, the receiver, why does that thing keep popping up? Must be hitting something wrong here. And again, the force law looks very much like the gravitational one. In the numerator, you have the product of the source and receiver. In the denominator, you have the distance behavior. And it just tells you the bigger the charge is, the stronger the force. The bigger the distance, the weaker the force. This force is attractive and repulsive. Benjamin Franklin did those experiments. This force accounts for the stability of atoms, molecules, and matter on the everyday scale. This piece of matter, us, we're all electromagnetic phenomena, basically. Large clumps of matter are held together by gravity. Most other matter is held together chemically through atomic molecular forces, okay? And it's the electric force that actually does it. So each force has a purpose here. The gravity, large scale, electricity and magnetism, everyday scale, atomic scale as well. The strong force, why do we need this thing? Even before I do any of this, let me just put this up a second. It's getting hot. I'll take this guy. I'm not connected from the inside. If you're familiar with the classic view of an atom, where you have a nucleus and you have electrons out here flying around, inside the nucleus, we're told, are all the positive charges, and the negative charges are out here, and they balance with the electric force, and that gives you the stability of an atom. But you have these positive charges in here, inside this guy. Benjamin Franklin told us positive charges repel one another. How could they be inside a nucleus? They repel. Does everybody remember that? Like charges repel, unlike charges attract. You can take a piece of glass or a rubber rod and rub it with silk and do these experiments and verify this in your kitchen. Why are these guys all stuck to one another in here? We have to invent a new force, necessity. We just have to do it. So we have the stability of an atom all straightened out, and molecules and how compounds are made this way by the electromagnetic force. But now you got the nucleus, and some of them have a whole bunch of protons in there, all stuck together, not flying apart like Benjamin Franklin said. Why? New force. How big is this force? Big. It's stronger than the electromagnetic. Certainly stronger than gravity, because the electromagnetic is stronger than gravity. A magnet can make the keys jump up. This force has got to be able to overpower the electric repulsion, and it does. So we invent it. Now, anytime you invent something, it's got to do more than just explain the current phenomena, and it does, but I'm not going to go into all the others. But the source of the force, receiver, the distance behavior for this, like Scotch tape. It only works when they touch. Because that's what we observe. You take two protons, or well, it doesn't work with electrons, but two positively charged particles like protons. You start to force them together, and Benjamin Franklin force, the repulsion, is giving you a hard time here. They don't want to come together. They're light charged, they repel. If you're strong enough and get them close enough and they touch, you can let go. They stuck. So the force only works under contact. So I call it a Scotch tape force. And the range is about 10 to the minus 13 centimeters. 1/10 trillionth of a meter. That's how close you got to get the protons together before they stick. So you can start building nuclei this way. Just sticking things together. As long as you can get the energy to push them close enough together, they'll stick. Stop me anytime with questions, okay? What is the source? It's a name, don't worry about it. There's a source of this strong force. Something gives rise to it. The technical name is color. Don't worry about it. There is a strong charge, just like mass, just like electric charge. There's a property of matter that generates this force. What is it really? Same question. I don't know what mass is really that generates this attraction. I just don't know. I don't think anybody else does either. You think? I don't think so. We have an expert particle physicist in the audience, an expert astronomer as well. Don't look around, it's you. Andre Perge. Source and receiver, same thing. What is the force law? I don't know. When things only act in a contact way, it's tough to write down a distance behavior because when they're touching, it's on. When they're not touching, it's off. If they're a meter apart or 20 miles apart, it doesn't make any difference. They don't see one another until they touch. Just like you're walking around with Scotch tape, looking for someone else with Scotch tape on their phone, and you touch. You don't see one another until the contact takes place. So we don't write a force law down for this. It's attractive and repulsive, and it allows the nucleus to be stable. We invented it so the nucleus becomes stable so they don't fly apart, because they don't fly apart. So we had to invent a new force. And we see it elsewhere too. Next one, weak, same thing. This is even shorter range. Don't worry about the name of the source. Don't worry about that. There is something in matter that creates another force inside the nucleus. Now, why do we need this one? Three's enough, my goodness. Why do we need another? We've got stability of the nucleus, we've got the stability of the atom. Well, someone noticed when the nuclei get large enough, they become unstable. They become unstable. A strange thing happens. I was about to write on this. Inside this nucleus, there are also neutrons. Particles that have no charge. And they sit around in here too. And the bigger nuclei, it turns out, undergo spontaneous transmutation. Something sort of science fiction. One of these protons spontaneously becomes a neutron because it felt like. It just, boom, transmutes itself into a neutron. We see an electron fly out of the nucleus and another particle which we don't need. Okay, a neutrino. Now we got ahead. We've got electrons, protons, neutron, and neutrinos. What are they? We had to have them because we see them. Now we have to explain them. There must be another force that contributes to the instability of the heavier atoms and accounts for this spontaneous transmutation, where a proton changes itself into a neutron, an electron plus a neutrino. It's a spontaneous creative process, actually. We'll talk more about that on the next slide. So there are the four forces. What's the force law mathematically that I can write down? I can't write it down. It has more to do with how things interact at small distances than it has to do with writing a formula down that has a distance formula in it. There are other things involved in describing these forces that we may talk about later. And it's responsible for explaining radioactive decay and the instability of some matter. All right? So those are the 4 forces we need. That's kind of dramatic, actually. You only need 4 forces to describe all the events we see. Only 4. That's not bad. Einstein, in the last 20 years of his life, tried to develop a program where you only needed one unified idea to describe everything. See, physics is easier than history, you know? You got to remember a lot of stuff in history. If we succeed in unifying these forces, you got to remember one principle. What are the range of these forces? We already alluded to that, so I can run through this pretty good. Gravity, E&M, strong, weak. Gravity force is infinite. It could be very weak when you go a little bit far away. You know, the distance is in the denominator, and that doesn't go to 0 until r goes to infinity. So that's why we say it's infinite. Long, very long range. E&M is infinite. Strong, short. The weak, it's even shorter. But I want you to remember back now, in the first slide where I said, at some point in time, namely at 10 to the minus 44 seconds, all the matter in the universe was clumped in a distance less than 10 to the minus 34 centimeters. That was the whole universe. All these forces basically had the same range. Infinity was only 10 to the minus 34 centimeters away. There was nothing outside that. So all these forces basically had the same range. That's curious. And the range was shorter than any of these numbers. 10 to the minus 34 is the size of the universe at that point in time. So certainly the weak force could be felt everywhere in that early universe. Strong force could be felt. E&M could be felt. And gravity could be felt. If they existed at that time. They all had the capability to be felt everywhere in that minuscule universe. Something I keep in there. The strength of these, I alluded to that too. The strong is the strongest. The weak is not the weakest, however. If the strong had some value 1, then I'll relate the strength of the others to that. E&M is about 100 times smaller. The weak is incredibly smaller, 1/10 trillionth, and about 1,000,000 trillion trillion trillionth smaller is gravity compared to the strong. However, if you go back to the early universe, that's the size of 10 to the minus 35 centimeters, with all the mass in there, what force you think may dominate that universe? The distance is only 10 to the minus 35 centimeters. The gravity force is going to be huge in there. In fact, I'm going to show you, the last thing I'm going to show you is that as you go back to earlier and earlier times, all of these forces meld into one. They are in fact uniform, which was Einstein's dream, and everybody thought it was nuts, playing God, trying to unify all the forces of nature. But it seems that that's what happens, actually. At early times, small distances. Okay, we got strength. Now I'm going to try to answer the question about the keys. If the Earth doesn't touch the keys, how does it affect these keys? People thought at one time, or they made a model, and they said, okay, we can do this. The Earth creates a gravitational field. Anybody hear that phrase, gravitational field? The Earth creates a field outside of itself that affects things in the space around itself. If the space is empty, like in the moon is an empty space, right? How does the Earth affect nothingness? If the space is empty, that always troubled me, actually. And it troubles a lot of people, but we talk about it anyway. The Earth creates a field around itself that allows us to talk about how it affects the keys. So it's the field that touches the keys, some invisible field, pulls the keys down. And that was fine for people to describe the gravity force and the electromagnetic force. It's not so necessary for the strong and weak because they're basically touching already. You know, so we don't need to have this thing that does something for all of space around it, for the strong and the weak so much. But this model of the mediator is going to work for them too. So in 1949, Feynman, Tamanoga, and Julian Schwinger said, you know, the Earth needs to touch these keys in a direct way. And they have a model, seems to work, where the Earth shoots out particles that you can't see. You can't see the air either, though, can you, Ryan? You don't see the air, do you? The Earth shoots out particles, taps on the keys and says, you're coming down. And it pulls them down. Charged particles, same thing. Two like charged particles. They exchange physical particle entities. Out of one electron, something comes out, goes to the other electron, physically hits it, and says, back up, we're repelling. And it does. There's a direct contact there. So you're right to question me when I wiggle my finger and the keys move. Something must touch those keys. The Earth must touch the keys. Like charges must touch, even though it seems like they're acting through empty space. Something's going from one to the other. Those three guys won the Nobel Prize for this model. And that then requires mediators, informants of the existence of particles and things. The mediator comes out though. And they have names. They're irrelevant. But what I'm telling you is the field concept has been replaced by a direct touch again. The keys are directly touched by the Earth. The moon is directly touched by the Earth. Okay? By particles that are streaming toward the moon. And back again. The moon's shooting stuff out of us too. They have names. These are just names, all right, of these particles. Do we see any of these things? We see photons. We see weakons. We don't see gluons. We don't see gravitons yet, all right? Yet. We may. They're just names to indicate that, look, the idea of empty space and something acting on empty space doesn't make a lot of sense. You need an actual touch going from one thing to another. And at the bottom, I reiterate that. Exchange particles, 1949, versus action at a distance, field concept. You can jump in a tub tonight and do the same thing. Put a cork on one end and splash the tub. And eventually a wave will go out and affect the cork without me actually touching the cork. That's this field concept that people say, oh, gravitational field is set up. Well, that's fine if you have a medium that'll react to the mass, but if you're in empty space, it's hard to make that analogy. But that was what people were thinking about, right? That there's something out there. Well, there still may be, but that's another story. So far, what do we have? Okay. We're trying to explain all the things we see in nature, and I'm approaching now just the particle physics part of it, where we're looking at everyday life, looking at the forces, and then drilling down to smaller and smaller distances. And I'm not thinking about the cosmology yet in the beginning of time, but I'm making references back and forth now and then. What we have so far is electron, proton, neutron, neutrino, and the four mediators, or the four forces. So there's there are about 8 particles that we need to build the whole universe, it seems. So we get clever and we start picking at these particles with one another. We'll fire an electron at a proton, fire a proton at a proton, neutron at a proton. Strange things start to happen. The old adage, never ask a question that you don't want the answer to. You fire a proton at another proton at a high enough energy, you get 2 protons out and a whole shower of other things come out. It turns out that the proton has parts. You look inside a proton, it has 3 parts. How do we know that? We can't get them out, but we know there's 3 parts in there. Consider this. I have a bag against the back wall. There's 3 billiard balls in it. I don't know that yet. But I know something. I have an inkling that, look, it has extent. There may be something in there. It appeared that the proton was about 2,000 times heavier than an electron. It appeared a little bit bigger in some experiments. So I take a BB gun and I start shooting the bag. Particle physicists have a lot of fun like this. Yeah. Shoot the bag up. Look at the shadow of the bag. I'll see a shadow of three things. Without looking in the bag, I can create a shadow where the electrons couldn't penetrate the billiard balls in the bag. So I see a shadow of what was in the bag. So you can do particle physics experiments like that. So you shoot at protons and discover there's three things in them. I want to get one out. I'm real anxious. So I crank up the energy. I start firing more and more energy at a proton, either use an electron or another proton. I try to rip one of these innards out, and they're called quarks. There's three quarks in a proton. So now we've got more particles to deal with in the story, see? Trying to rip this quark out, in the effort to try to rip it out, it takes a huge amount of energy, we think. But before we can rip it out, something very weird happens. We have spontaneous creation of other quarks. We can't get that quark out, but pairs of quarks start to appear all over the place. It gets a huge shower of these quark pairs, and other particles come into existence spontaneously and then decay away. They don't live a long time, these things. You put energy into a local place in space, particles are created, actually created from energy. I'm being a little dramatic with that because it excites me. All right? It's Einstein's famous equation equals mc squared. Yeah.
Well, is the particles that you're creating coming from the energy you're putting into the system?
Yes. Energy is directly transmuted into mass. Right, exactly. Now, why is that mass scheme come into existence? That's a good question. You know, you have this scheme of particles. Let's go. I'll show you what they are. The next step is the particle zoo. A whole zoo breaks loose of particles. I'm just going to mention what they are. Protons and neutrons have parts. There's quarks in them. Probing them at higher energies, I just said all this. You get spontaneous creation using Einstein's famous rule, E equals mc squared. Pump energy in, you can create mass. Why that particular mass? Some have the mass of a proton, some have 5 times the mass of a proton, some have half the mass of a proton. Why is that mass scheme come into existence? That's a good question. Where was it hiding? Why no other masses come into existence? These are the why questions that physicists are starting to ask. Why that particular spectrum of mass that comes out? There's 140 mesons. Don't worry about what mesons are. Just look at the total number of things that we've discovered. 140, 120, the 4 mediators, and a whole electron family. There are like 300 particles. Going from what we started with, electron, proton, neutron, neutrino, and the 4 mediators, 8, we have 300 now. We've not solved any problem. We've got more complex. All right, more complex. It's frustrating. This happened in the mid to late 60s, 70s. This stuff was coming out all over the place. This is when I was in the field. That's what drove me out. Just was going nuts with this stuff. Right? You had the same question, yeah?
You said we have about 140, 120. We have more of these. What are you calling those things?
Well, I can give them names, okay, but they're all made up, I'm going to show you the next slide, of 12.
Is there a category that covers them all?
Yes, that's the next slide. We can make them all. These all came into existence. We categorize them, measure their properties, just like you collect butterflies and things like that, and then you eventually categorize them. That's why I call it the zoo. We were just collecting them in the 60s and 70s, finding them.
Is that the makeup of things?
Yes. Well, these things don't last very long. The makeup of things are basically atoms. When you probe the very small at very high energy, you create matter that doesn't exist at the everyday temperatures that we have. But if you go way back in time where the temperatures are very high, these things are created then too. See, when we look at the very small, it takes higher and higher energies to do it. Now, I want you to equate higher energies with earlier times and higher temperatures. Same thing. So the particle physicists, as they drill down to smaller distances, they're creating particles that don't exist on the everyday level, but may have existed eons ago in the early universe when the energies were that high and the distances were that tight and the temperatures were that high. So that's where the connection comes in. Good question. But if you want to name them, yeah, we can build them all. Here's some examples, and you can see they're quarks. Make them up. Don't worry about this. There's a pion, kaon, rho, A to C. These are quarks, names of quarks. Up, down, strange, colored. Don't ask. Here are baryons. Don't worry about them. How many do you need? You really only need 12. This was your question. I can build all those 300 or so particles from 12, but it's a lot bigger than the 8 I had. That's still not a nice situation. 12 particles plus the 4 mediators. There's this electron family, and then there are the quarks, okay, that we found inside of protons, and that's it. That's not too bad. That made people pretty happy when we can build everything from 12 things. The effort in particle physics was to find the fundamental building blocks in nature. What are they? What can we build everything else from? From this, we can build the 300 particles that come in these showers, and we can build protons and neutrons, and the electron's fundamental. All right. So we can build everything from these 12 guys. And the question is, how many do we really need? 12 plus 4? Next question is, how many do we really need? And this was the question posed in the early 70s, I guess, by Vincenzo and some others. They developed some theories that looked really weird. And they were discarded until recently. And people start to look at these theories again, and about unification, and about cosmology, and things start to make sense. We're banging against very small distances. Early universe has very small distances, high temperatures. Something's going on here. How many do we really need? 1. We need 1 particle. That's it. That was Einstein's dream. 1 principle. What is this thing that we only need 1 of, that somebody has this model for? Has a name. The name is string. It's called a string. It's one-dimensional, has length. Its size, you could have guessed this, 10 to the minus 35 centimeters. That is the size, smaller than which we know nothing about the early universe. Okay? Has a name called the Planck length. These strings could be open or closed, just like any string can. It can just be sitting here. It can be closed and form a ring, and they wiggle. The number of wiggles changes their nature. Okay? How they oscillate and jiggle could be a proton if it jiggles one way, could be a neutron if it jiggles another way, could be 1 quark if it jiggles one way, another quark. All we have to do is to get it jiggling, and we can create any particle from 1 string, 1 principal string. This is far out, this thing. So as it goes through space, imagine that this width is 10 to the minus 35 centimeters, 10 to the minus 34 centimeters. It could be open-ended or closed-ended, and it's going to be jiggling, wiggling. The vibrations, the theory of the vibrations, which is incredibly complicated, generate not just all the particles. It predicts the mass sequence. It predicts electric charge. It predicts mass. It predicts the strong interaction property. It predicts the weak interaction property as well. Powerful, I'd say. It unifies all the forces. There's only 1 string. From it, we can derive the properties of all the forces in nature. Now, let's go back to those other forces and see why they weren't successful at this in some regions, namely the region that's very small. Why isn't gravity successful at distances below 10 to the minus 35 centimeters? Why aren't the other theories successful in those regions? And it's as fundamental as Newton thought about space and time, as Aristotle thought about space and time. Comes down to that. What is really space and time? Let's see if we can do this. When I say point particle theories, here's 2 electrons, right here. And this is sort of like a time diagram, space diagram. The particles are coming up, they see one another, they repel. Don't worry about these other guys. This is the strong and weak interaction, basically the same kind of a thing. Here's the mediator. This electron spits out a photon, the mediator for the electric force. It hits the other electron, it recoils. Repulsion. Note, however, that it happens at a point. The model, the mathematics of this theory requires space to be continuous. It requires the mathematics of calculus, differential calculus, where the limits are taken to zero. It requires point interactions at an actual point in space. To us, that's physically unacceptable most times. Points don't exist. Go back and look at your geometrical definition of a point. It has no extent. How can anything happen in a place where there's no extent? But yet, the mathematics of this theory require it. That's the limit of our mathematics. It's a point theory. Things happen at a point. And that's what gives us trouble, actually. When we go down to the very small, just a real easy thing. If I had a force law that was, let's say, m1, m2 over r squared, as r goes to 0 to get down to a point, like at the beginning of time, if everything collapses to a point, what happens to the force?
Skyrocket.
It skyrockets. Anything over 0 becomes infinite. The mechanics of point interactions have infinities in them. When you really want to ask what happened at that point, the mathematics predicts infinity sometimes, all right? The center of a black hole. Okay, you know what a black hole is. You heard of a black hole. Incredibly dense object that towards the center, the density goes to infinity. General relativity can't explain it because the equations of general relativity, when r goes to 0, go to infinity. It's a point theory. The mathematics requires that you deal with these points. Gravity. This is really strange. I already talked about this a little bit. At the Big Bang, at t equals 0, we can't go there, it seems, at t when it actually started, because it requires us describing the equations at 0 distance. And at 0 distance, things become infinite in these theories. Mathematically go to infinity. Black holes, the center of them infinity. There's another really weird thing that happens. And I didn't talk about this yet. This is another fundamental principle in physics. We have the 4 force laws. There's another very strange thing. It's called the uncertainty principle. And philosophically, it changed the nature of physics in the 1920s. It says basically this. When you make a measurement, the measurer and that which is measured affect one another. You cannot talk about the measurement without the measurer. And that becomes obvious when you go and drill down to the very small. If I want to know where an electron is, that's a very small thing. What do I use? I can use another electron. I can't use a baseball bat. So I fire another electron at the first electron. Affect the speed and position of the first electron. Put yourself in a room with a billiard table that has no pockets. I want to put the cue ball on a table. I'm going to blindfold you. I'm going to give you the 8 ball. I'm going to say, find the cue ball. Now I'm giving you a measuring device that's the same size as the thing you're trying to find. So you're very clever. You start to march out the measurement from one side of the table to the other. So I'm going to slide this down the rail here. I'm going to move over 1 ball length. Do it again, do it again, do it again. Ah, I hit the ball. Good. Now you knew where it was. You don't know where it is now, and you don't know how fast it's going. So Heisenberg said there's a fundamental limit to how well we can know things. And as you close in on space, as you start to look at smaller and smaller pieces of space, space itself revolts against you. Okay, if I'm trying to look at a gravitational field in space, and I think space is very smooth, and I'm trying to localize that field, it starts to oscillate violently, just like that cue ball did when you try to hit it. So when you get to distances of 10 to the minus 35 centimeters, space looks like this. That's what people think. Anyway. Space looks like this foam, this agitated foam at that scale. All kind of crazy stuff is happening. Because the act of isolating space to that small size creates energy. And you get this violent reaction at that scale. But gravity only works if you have a smooth space. Gravity doesn't know what to do with this. Einstein says space-time bends smoothly. This quantum foam business with the uncertainty principle, when you try to localize space, space actually starts to break up. And time breaks up into chunks of 10 to the minus 35 centimeters and time 10 to the minus 44 seconds. Space itself gets ripped. What's that mean? Space is quantized. You can't arbitrarily go to smaller and smaller spaces. There's about 30 people in this room. That's an integer number of people. I can't go to 29 and a half unless I kill somebody. All right? It loses the identity. Same here. You cannot go below 10 to the minus 35 centimeters. Is what we're going to say about the string theory. The string is the smallest thing we found. I can't measure anything smaller. It means space comes in clumps of this size. And time comes in clumps of 10 to the minus 44. Space and time is carved up in a non-continuous way. You can't do the old thing and say, well, take thing in half and then half it again and half it again. You can't do that. You can't go down to infinity. That doesn't happen. You can't go to infinity. You get to this scale and you must stop because you can't measure anything smaller than the smallest particle you have available to you, which is a string. Yes?
These are essentially fundamental particles of space, fundamental particles of time.
Yes. Yes. That solves the initial problem in the Big Bang Theory. Why is this wall at 10 to the minus 35? Because space and time are not defined smaller than that. I couldn't measure anything smaller than that. General relativity doesn't have a problem then. It doesn't have to explain this foam. Guess why? You will never see it because a string can't detect any of this. This was a conjecture due to an uncertainty principle that says you can go to zero position. String theory says you can't. You can't go to zero position and in turn inflict huge energy fluctuations in space. You can't do it. Strings look like this. They don't look like point things. They come wiggling along. They always occupy a finite amount of space. So there's no points when they start to hit one another. There's no singularities. It never goes to zero. I don't worry about the uncertainty principle below 10 to the minus 35 centimeters. How convenient is that? It's not a particle theory, a point particle theory, like gravity and quantum. Distances smaller than a Planck length are not accessible. Can't see them. No singularities. Space-time is quantized. That is an incredibly strange concept. Space is not continuous. Time is not continuous. You can't arbitrarily cut time up into smaller and smaller segments. You can't cut space up into smaller and smaller segments. It doesn't happen because you can't measure it. If string theory is correct, it may be wrong. Probably shouldn't have said that yet, but it's all right. How do you deal with this? You can't use the mathematics that you use for quantum mechanics and most of gravity. It requires a geometry of quantized space, of discrete space, the ability to handle mathematical operations and not, those of you who had the calculus, not let the limit go to zero. You can't do it anymore. You can't let the limit go to zero. It's got to go 10 to the minus 35. How does that change things? You need a whole new geometry for that, is the point. It's easy to talk about, difficult to calculate. You can go away from here tonight and know that, gee, there's one particle, there's a string, predicts everything. Can you do it? It's very difficult. Gee, there's one missing. Oh, there it is. Yeah, we can predict, it hopes to predict all the particle masses and properties. This is the one, that's why it came up last. It does something very weird here. It predicts 10 spatial dimensions and time. We live in 3 dimensions. And this theory predicts 7 extras. Where are they? Guess what? You know how big they are? 10 to the minus 35 centimeters. They're rolled up and crunched up into a space 10 to the minus 35 centimeters. Guess what else? At early times, way back, all space was rolled up into 10 to the minus 35 centimeters. That's as big as the whole universe was. Everything that existed in a space of about 10 to the minus 35 centimeters. All 10 dimensions were that big. The question now gets removed one step back. How did the 3 dimensions we're familiar with come out of that soup of rolled up dimensions? I don't know. But it did, luckily for us, huh? But what are the other 7 doing now? They're rolled up hiding in distances of 10 to the minus 35 centimeters, and you can't go there because I just said you can't. Because strings are that size. So this could be a big hoax. Okay, here's the last slide, and this is what I want to show you. We're going to finish a little bit early. Here are the force strengths, and as you go to shorter and shorter distances, they all approach the same strength, which makes sense. If everything's wrapped up in the 10 to the minus 35 centimeters, the range of all the forces are basically the same. All right? I want to give you a bigger picture of this. It's the history of the universe. This is what I wanted to show you. This is what I was talking about a little while ago, where everything is summarized here. You can spend a week on this thing, but you can't see it. I'm going to see if I can get a bigger one up for you. I have it in here. The history of the universe. There it is. Let me try and take you through this. Here's the Big Bang. You can see that. This is the present day over here. The scale is not equal increments of time. All right. Most of the scale is taken up with early times. You probably can't see this. Let me read it out to you. Here's a 10 to the minus 44 seconds right here. What happened before that? We're not sure, but the name of the game is if strings are true, it's irrelevant. We don't need to know. The temperature there in the early universe is 10 to the 32 degrees. Again, it's almost a trillion degrees, if you can imagine that. A little bit later, 10 to the minus 37 seconds, that's a short time later, something very strange happens. You get this huge inflation of the universe. It spreads out to here, very rapid. This is mostly energy here. Here, something called the Higgs field settles out, and particles attain mass. Okay? I'm just stating things now. I'm not going to go beyond that. Here are different epochs. This is only 10 to the minus 5 seconds. This is about 300,000 years here. The universe was opaque up until this time, 300,000 year mark, because what you had were light nuclei, light, and some of the quarks and things floating around in a soup. Light couldn't get through. Once it cooled enough to form hydrogen atoms, for instance, immediately the phrase "let there be light" happened. The light that was all pent up banging around in this fog broke loose. The universe is now transparent at the 300,000 year mark. Now, from 300,000 years all the way out here to 11 billion, not much is happening. All the action happened here. So that's what I'm saying. This time scale is not linear along this way. So atoms form, stars start to form, and we know how that happens. This hydrogen and other lighter things start to condense. Gravity pulls them together. They start to get hot. They're getting close to getting hot. Nuclear fusion starts inside these things. Heavier elements form until you get to iron. the impress of gravity is counterbalanced by this nuclear bombs going off inside these stars. When you get to iron, that can't happen anymore. Gravity crushes them, they explode, and the rest of the elements are formed. Our star's a second generation. I'm saying an awful lot very fast here, sorry, but our star's a second generation star. It has all the elements in it. Our Earth has all the elements in it. Okay, because the elements were formed after this first generation star exploded. Anyway, we know how stars work, we know how galaxies form, that happens here. And here's the present day right here. So I think you can, I'm going to ask Andre here. With various detection techniques in the night sky, we can see almost back to this epoch, I think. Is that correct? We can see, right. We can see back to when the universe became transparent. So we could see back to t equals 0 plus 300,000 years. So this is almost 11 billion years. We can see in the night sky to here. All right? We can't see beyond that because the universe was like a fog. Bottom line is this. The string theory, which is what I'm talking about here, could be the theory of theories, the theory of everything. You see books like that too. But this also happened around the 1890s too, that the physicists thought they had it all done. We got it all figured out, but we didn't. This is rather beautiful though, because we think we know what happened all the way back to 10 to the minus 44 when we started this lecture. The string theory proposes to say what happened before that time. And there are some folks who have bootstrapped this string theory into membrane theory. I'm not going to go into that. Paul Steinhardt from Princeton gives a great talk on this. People start to ask, well, what happened before the Big Bang? See, but we weren't commissioned to do that, right? We just, how it began. But people do ask that question. Well, gee, what happened before the bang? Paul Steinhardt claims there have been many Big Bangs. And this diagram sort of like hints at what's going to happen here. This is a straight line here. But the universe seems to be bending out from this straight line. It means it's expanding, it's accelerating. Paul Steinhardt seems to say that this expansion is due to this negative gravity that we're not unaware of here. And eventually, in about 1 trillion years, the universe will cataclysmically start again. Another Big Bang will occur. He's got a model for that. So what he's saying is the universe, quite possibly, is cyclic. It happens over and over again. And the time cycle, about 1 trillion years. That is incredibly fascinating to me, actually. I mean, people were excited in 1967, 68 when Penzias and Wilson discovered this background radiation coming from this time when the universe became transparent. And a lot of theologians, actually, and philosophers got excited about that because it implied a beginning. Einstein thought that the universe was eternal, never changed, stayed the same, nothing ever happened to it. No beginning, no end. So people were very happy that a beginning is inferred. For the theologians and philosophers, it implies a cause outside the universe that started this. Now we're getting into philosophy theology. I always question, gee, why did God wait till just 11 billion years ago to do this? He's been around forever, you know? Why did he wait? Well, Paul Steinhardt's idea of a cyclic universe answers that question for me anyway. He's been doing this forever. It's been starting, stopping forever. I kind of like that idea from just a philosophical point of view. There is problems with it from the physics point of view. There's an entropy problem, which I didn't talk about, that this will run down. There is a finite number of cycles that Steinhardt's model can do. But I like the idea there's more than one universe. So that's where we are. How did the universe begin? I'll go back to my first answer. I don't know. I don't know. But we know an awful lot after the initial start. We can explain an awful lot. And if string theory pans out and we have the quantized geometry to do it, we're going to know a lot more. Thanks so much. Any questions? Any discussions? Yeah.
This model, the cyclical model, is that a model for trillion years before that Big Bang?
Yes, as what he's saying is this has been going on many times. So many trillions of years have transpired.
But it's the same kind of development? Or evolution.
Well, yeah.
And so if this dies, this universe dies, and starts again, it would follow that model?
That's not clear, actually. Something else is going to happen. There will be another Big Bang. There will be energy. The life forms may be different, who knows? But the physics principles are going to be the same as in this universe, or else you couldn't make the model. But what kind of other things evolve, who knows? I don't know. But that's one model. I guess he and Guth is the other guy who proposed this.
Yeah, Alan Guth.
Guth proposed the cyclic. You had a question, Scott?
Yeah, I was going to ask you, I mean, the Planck time and the Planck length.
Yeah.
How do physicists know that that's intrinsic to the physical universe and not a breakdown due to limitation of either measurement or due to limitation of mathematics?
You just take the uncertainty principle, delta field, delta change. You let one go to 0 and it implies the other goes to infinity. Okay? We know we can do general relativity down to that 10 to the minus 34 centimeters. We know that. General relativity actually works down to that. So that's the natural barrier of general relativity. That's why we picked that number. Now 10 to the minus 44 is the time it takes for light to travel that length. So that's basically falls out. Now the Planck length can also be gotten from a combination of fundamental constants. C, H bar, G and stuff like that. It pops out. But basically it's the limit of applicability of general relativity. Bangs against 10 to the minus 35. So somebody says, well, why try to bang against it? Let's say you can't go beyond that. Let's invent a string that's that size. So you don't see the quantum foam.
Plus, if someone came up with a different theory of gravity, would those numbers
They may change, sure.
be smaller or something?
Sure. Yeah. Exactly. But current general relativity, that's the number we're banging against. Yeah. Good question. Yes?
Are the mediators going faster than the speed of light?
The massless ones go to speed of light. The ones that have mass go slower than the speed of light. The mediators. All right, that's it. Anything that has mass can't go to speed of light. In fact, curious light, the light that came out here, if you had a clock on the photons that were coming out of here, that clock is stopped. Those photons didn't age in 11 billion years. Photons don't age. Time doesn't pass for photons. That's it. Just doesn't pass. Time doesn't pass. Physics is weird, isn't it? Any other questions? No.
How long have people been working on the string theory?
Since 1967, Vinciano proposed this model that has a part of it non-point-like phenomena, that things were finite in length and the calculations are horrendous. People dropped it until the 90s, I guess. You're more recent on that. I got out of school in the 70s. But when did string theory real emerge? 96? In the late 90s, they started saying, wait, this may have something to it because it maps onto reality. There are no points in reality. You can't talk about a location in space that has no physical extent and expect to get something physical out of it. But the mathematics of finite pieces is very difficult, so people have a hard time dealing with it. So it's not that long, actually. So 67 initially, and then about 95, 96 again, people picked it up. Now this fellow Witten has, there were 4 or 5 theories of strings, and Witten has shown that they're all equivalent, actually. So, but they still haven't worked out the mathematics of it. So it's very hard to do calculations. There was a question up here somewhere? Yeah.
Yes, I was wondering, in August there was an announcement out of University of Minnesota about cool spots, very large cool spots in the microwave background, the background radiation you referred to. And I'm wondering if those observations will support this model or contradict.
String theory predicts inhomogeneities in the background radiation very nicely, actually. maybe not the biggest one they just found. There's a huge void somewhere that they just discovered. I haven't heard anybody talk about that yet, but string theory can account for the inhomogeneity of these and what we see presently without really having a rapid expansion called inflation. Paul Steinhardt's model doesn't require this rapidly expanding universe early in time. Okay, the details of that are complicated, as I said, but string theory can account for cool spots. Any other questions? Yeah.
Could it be possible that one of the explanations that gravity is so weak is that it's dispersing into some of the other dimensions, like the 11th dimension? Is
Yes,
that possible?
exactly. No, it is. People have that thought that gravity is the only force that permeates all 10 dimensions. E&M doesn't, weak doesn't, strong doesn't. Gravity is the connection with all the dimensions. It's unique gravity, very unique. And it could be weak in our 3 dimensions because it's taken up in the other 7 as well. Yes, that's a good question. You read that, right? You heard about it somewhere? Yeah. I heard about it too. So I'm just echoing what you just said. Right? True, yes.
Do theories of dark matter enter into these considerations?
Yes, I didn't talk about it, but string theory actually talks about dark matter and dark energy. Dark matter is not so complicated. Dark energy is weird. Dark energy is basically gravity that's repulsive. All the gravity we know is attractive, but dark energy, theories of dark energy translate into gravity that repulses. Okay, and that seems to be what's going on, sorry. During the inflation, the people who have the models of inflation, this dark matter, dark energy, is repulsing and it overcomes regular gravity. Regular gravity then dominates again over here, but it looks like dark energy is pushing us away from this straight line and causing the universe to accelerate again. You would think over time that after an initial explosion, like if I throw the keys up in the air, they come back down, right? You would think after an initial big bang, gravity starts to pull everything back after the effects of some initial explosion. So they're starting to measure that effect. Is the universe starting to slow down? No, it's not. It's bending away again, so it looks like it's expanding quicker than it should be, which means this dark energy is starting to dominate again for some reason. And I don't understand why. Yes?
If it has been found that when there's very high energy, very high temperature, all sorts of particles are made spontaneously, are there any ideas how long everything could stay in a point of single?
Oh yes, yes. These theories have to predict the lifetimes of these things. Exactly. You know, you create a particle, it lasts for a certain amount of time, and your theory should predict the lifetimes. That's exactly what's required.
Oh no, I meant how long, if there was everything's in one space, how long before are there any ideas how long it would take for the Big Bang to occur?
In other words, you're assuming that there's matter being agitated and all of a sudden a bang happens.
Well, no, I'm just saying if everything that's now out was all in
a space like over here, right?
Yes.
It's a very tight space. Why did it bang? I don't know. I don't know. I said that on the first slide. I have no idea. That's a good question because you have this incredible gravity at that point. All the mass of the universe is in less than 10 to the 35 centimeters. That's an incredible force holding it in. There must have been an incredible force in the opposite direction, okay, this negative gravity that pushed it out. I don't know what caused this Big Bang. Do you, Andre, can you say something about that?
Not really. I look at it from another point of view. Initially there was energy, right? So where's gravity?
Well, energy has mass and mass has gravity, so that's...
Right, but energy, in the energy form of view, like the frequency of a photon, doesn't gravitationally interact. That only complicates things further, because
right.
you say gravity is the dominant force, and I will sign to that. But I don't see where are the particles that would interact with such a... Where is
Right, there are no
everything?
mass, there's no mass yet because the Higgs mechanism is active. The Higgs mechanism's got to die off before anything gets cloaked in mass. And I don't get that.
So
I
what
don't
causes
understand.
gravity?
Yeah, but see, energy is mass, whether it's inertial mass identifiable in particles or if it's photons. It's still mass. I don't know. I just don't know. To answer your question, I don't know what caused the bang. I don't know what caused the bang. I don't know. Yes.
I do have one question. You said that roughly 300 particles were observed. Is that
Roughly.
it finally? Are we done or?
No, actually, I lied. String theory predicts 10 dimensions and a bazillion particles, but yet they still come from one. Now, these particles are huge mass particles. Where do they come from? Incredibly high energies. They may be buried in here too, and they're not in this diagram. We haven't found them yet, but if you look up here, these are actual physical locations where we're running experiments at these energies, okay? And there are some hopes that string theory next 10 years, I guess when this CERN LHC is done, there may be a signature there of one of the particles it predicts that we haven't seen yet. It'll be the first prediction of a string theory particle, that a very heavy massive particle. So you're right. We're not done. String theory predicts a huge number of particles, but you require huge energies or temperatures to find them. So we're just not there yet. But it's a good test, though, actually, I think, for string theory. String theory is either going to be confirmed or go away in the next 15 years, maybe.
Has it made any predictions so far that have been verified?
Yeah, it can predict the mass spectrum of a lot of things. That's true. But it also predicts stuff we haven't seen yet. So some string theories can predict an awful lot of stuff. Okay, the first thing it predicted, the very first thing, that Schwartz, I guess it was playing with this, and he saw that the theory predicts a spin 2 particle that's massless, and he realized it was the graviton, the mediator, the graviton. That was the first success, and that's what got people running with this again, and then other mediators were predicted, and then certain mass spectra were predicted, but it's predicting things that are not seen, so people are looking for them. Okay? That's as far as I know, anyway. I'm telling you, this is sort of a hobby with me. I got out of particle physics years ago. I'm trying to be an astronomer now.
This is one of the reasons why these things aren't seen, is because we don't have the instrumentation.
Right. We don't have the energies to create a particle of that mass with that energy. Right. But the thought is that the CERN LHC here may be able to see one or two of the particles that string theory predicts. And that should come online shortly. That's where we are with that. Good question. Any other questions? Okay, thanks again. I enjoyed the discussion.